I'm going to speak about toward agents with competence and learning. So I will start by a high-level introduction of the one we're speaking about, model 3, reinforcement learning and deep reinforcement learning. On this, we problem of understanding common sense and mental models, and how can we add those tools to our toolbox to solve the problem and finish like some future. So a very, very quick introduction to machine learning. Probably everyone knows what supervised learning is. It's the most common example is the one of image classification, where you provide a large amount of data, images, and labels, and you train an algorithm, by the arrow, that is able to look at an image and classify it correctly. In this case, it's a horse, but it doesn't do it in a single image. It has to be generalized to arbitrary images. Of course, it's like this one, or tend to even grasp at the idea where a horse is beyond just the animal, but maybe the characteristics. So this would be classified as a horse, or maybe with some with a wooden statue, and this would be also a horse sledding. And this issue of generalization of understanding beyond just the training data is a key aspect of correct machine learning. So this is supervised learning, where you've provided at training time both the question and the answer. The paradigm that we work with a lot at DeepMind is a slightly more general. It's called reinforcement learning, where we learn to make sequential decisions in some kind of environment, and you're only given a delayed and partial feedback. So the assumption, the framework is that the agent is going to take at every time step is going to receive some sensor information, which we call the observation, some feedback of how well it's doing so far, which we call the reward, and the agent, based on that information, produces an action, which is going to change the state of the environment. And the agent's aim is to maximize the sum of rewards. So this leads to a feedback loop represented here, where the world at the bottom sends information to the agent and the reward, and this reward modulates the learning of the agent that learns to produce actions that lead to the reward. So if I enroll that feedback loop, it looks something like this, where on the top you have the world that sends the observation to the agent. The agent forms some notion of internal state, which I call ST. And from that notion of the state, below the dotted line is the agent side of things. The agent can do some kind of action, and that gets to the environment, and the environment changes as a consequence of action. On the bottom here, the environment has changed very slightly. The agent also receives a sequence of rewards, which I denote RT, and we compute a quantity called the return, which is a discounted sum of rewards. The discount saying that we care more about the immediate rewards than the ones much zero. And you can set the discount to 1 if you weight all rewards equally. Okay, so this is the framework. This is the problem. This is what we're trying to solve in general. There is an approach to this problem which is called model-free reinforcement learning, where basically we're going to try to learn the mapping of states to actions without necessarily understanding exactly how the environment works. So we learn this here. I don't need to switch sides on the pointer. Oh, well. Okay. No, it works. Okay, great. Yeah, so as I was saying, the framework of model-free reinforcement learning and model feature really refers to the fact that there is no model of the world. The agent learns some kind of mapping from the states to actions which are to the reward. And a very, very quick high-level introduction of how these methods work. There's two large families of methods, policy methods and true learning or value-based methods. So the policy method says, the basic idea is to say you try something, and if it works better than expected, you measure the return that you get in the episode, and if it's better than you thought you would get, you try to do more of that action in this setting. Mathematically, I try to keep the math to a minimum in this talk, but we assume that we start from a state from which we compute the probability distributions of our actions. And we're going to sample that, we're going to try one action from that probability distribution. the return is limited RT, and we compute a function, we learn a function called the value function, which is a function of the state, and tries to approximate the return. So it tries to predict how well do I expect things to go given that I'm in this particular state. You do the difference between the actual return observed and the value, and so this gives you kind of a signed quantity, which if it is positive means things went very well, or better than expected. If it's negative, it went worse than expected. And so you change the quality distribution in the direction of that quantity. So if it went better than expected, you try to increase the probability of that action in that particular situation. A Q-learning method is related, but it's not quite the same. Here we learn a predictor of how well things will work for each action, and then we take the action with the best expected outcome. So we learn an approximation of the return, which is not just given the state, but the state and the action. So based on a state and an action, we try to predict the return, and then we simply take the action which is the largest expected return. Okay? So in classical quote-unquote reinforcement learning, these mappings, this mapping here and here were linear functions. The state was handcrafted from the observation. But if you want to build very general systems which don't require too much handcrafting from a person, from a domain expert, you need to learn to construct the relevant state. How do we find a good state representation from which we can do good policies, predict the rewards? And this is where deep learning comes to very useful. So what is deep learning? Intuitively, the idea is very simple. You take a bunch of simple components, and hopefully, even though they're simple, when you assemble them together, you can build stuff which is pretty cool. More precisely, most neural networks are a composition of linear transforms, so linear functions, matrix multiplication, and nonlinear functions. And from this composition of large graph of simple computation, you can get massive modeling power, massive capabilities. And these networks must be very large these days, but routinely use hundreds of millions of parameters, more potentially. And the learning process corresponds to tweaking the values of these linear parameters. And this is done by optimizing a loss function over data. I won't get more real-world experience with respect to the parameters. I won't get too much in the deep learning path. Of course, this is kind of a prototypical picture of neural networks where it's just sequence of linear, nonlinear, linear, nonlinear. Modern neural networks have considerably more complex topologies than what was done before. Okay, so how do you combine reinforcement learning and deep reinforcement learning? Well, I was saying earlier, we're learning the mapping of the state to the action. Here we're mapping more. We're also learning the mapping of the iteration to the state and the state-to-state transition. So all these red components now are more learned and are basically complex nonlinear functions. So you can learn to extract information from the environment that leads to a good state representation, even if the observation itself is not a very refined form of observation. For instance, pixels. Obviously, we look at an image to understand what's on the image right away, but from a mathematical standpoint, or from a sensory standpoint, an image is just an array of numbers, and it's not clear what are objects or what are the relevant concepts to extract from the image. This is what the neural network is in charge of doing. And the driving signal for the representation learning is the reward prediction and the reward maximization. So this is a very quick introduction for deep model-free reinforcement learning, and it happens to work very well. So in 2015, well, probably it's large enough, deep reinforcement learning was applied on Atari games, entirely from pixels. So no knowledge of the games was, no knowledge of the games or the rules or what are the relevant concepts or how does it work was given to the agent. The agent just observes the sequence of frames, observes rewards, and learns to build a representation and policies which act very well in environments. It's very, very good performance. In many games, they're not all superhuman, so better than the best human experts. A couple of years later, this was applied to 3D environments. This is enough, and so these are a variety of everything. Sorry about that. Would only take the laser pointer get started. Right. So there is a variety of environments, and they require a variety of skills, from vision, language understanding, potentially because there is an instruction vision on the language channel, manipulation, locomotion, memory, navigation. So for instance, in this environment you see, in this stone the mazes, these little landmarks on the walls. And really, space starts again. I'll stop using the corner. And so you have the landmarks on the walls that indicate you where these apples, the rewards, are. And so the agent is thrown in random parts of the maze and then uses these landmarks and effectively an internal map of the world to try to very quickly locate the reward. Example, the last example is more like 3D type of agents. You have to do the complex control, continuous control, so you have these little lines. You have these little walkers with a high number of degrees of freedom that learn to walk and manipulate these obstacles. Okay? So it works very well. Get out of this video somehow. Yes. Okay, so what's perhaps missing? So I say perhaps because it is not clear, how far they can push these techniques, especially through generalization. They can learn skills in a way that is often surprising to the researchers. But there's certainly criticism for these methods, and one common criticism is that the learning procedure is effectively based on a stimulus response mechanism. In a particular situation, you did something and that led you to a reward, and so you're going to try to do more of this. So a form of philosophical criticism would be maybe this form, and these are the vague statements, but does the agent understand its environment? What we need to understand environment is the question, but nevertheless, where is common sense? These are philosophical criticism. Practical criticism, two common criticisms, these methods are very data hungry. So effectively because they encounter most stimuli, the randomly trying to correct behaviors and learn to properly associate them, it takes a very, very long time. Another issue potentially is that these methods might not be actionable situations. For instance, in a very recent paper by OpenAI, they released a benchmark which is based on the famous video game Sonic, and what they tried to do is to train Sonic to play on a bunch of levels, and then they take that trained Sonic and put it on a new level and see how well it solves this level, and it doesn't do very well. It generalizes some, but it could be better. This criticism is maybe they're by no means the only people that made this criticism. Brandon Lake and Josh Enbaum, which were Harvard Commerce and MIT, wrote a position paper called Building Machines That Learn and Think Like People. And the argument was, despite the biological inspiration and performance achievements, the systems differ from human intelligence in crucial ways. Specifically, we argue that these machines should be causal models of the world that support explanation and understanding, rather than merely solving pattern recognition problems from learning in physics and psychology. Okay, so now it's to the question, can we make steps towards common sense and imagination? Of course, that title is a bit potentially controversial and a bit cheeky, but the idea here is to try to, we only started to scratch the surface of this question, but the idea here is to inspire ourselves from questions and potential partial answers from cognitive science and neuroscience and try to think, what are we missing? What are the new methods that we can try to come up with? What would be an operational definition of these words? What would be an algorithmic definition of these words? And how can we try to come up with new ideas to solve a more complex problem? So maybe rather than imagination, the proper term would be mental models. So Kenneth Drake, which is philosopher and psychologist in Cambridge, gave, I think, this beautiful definition of what a mental model is, this beautiful hypothesis for how maybe the parts of human cognition work. And he says, if the organism carries a small-scale model of external reality and of its own possible actions within its head, it is able to try out various alternatives, conclude which is the best of them, reacts to future situations before they arise, utilize the knowledge of past events in dealing with the present and the future, and in every way react to a much fuller, safer, and more focused manner to the emergencies which face it. I have to point out, not everyone agrees with that point of view. Like this idea that we have this rich, basically projection engine that are able to simulate the world. There's a recent book I've only started reading, so I can't. These are based on me skinning the book, but called The Mind is Flat by Nick Chater, who's a professor at Computer Science University of Warwick, and he says effectively that cognition is intentional, processing one thought at a time, in a very similar way to perception. And effectively, our brains are our mind is model. And that all these ideas of emotion, goals, and desires, and so on, and models of the words are illusions, and that they're post-hoc explanation of our and others' behavior. But that's not the way we actually function. He bases our argument on a large collection of experiments. I tend to be on the side of mental models, but I think the true answer is that we don't know. Okay, so we already have an example actually of reinforcement learning technique that's performed very, very well, and that it uses the model of its environment, which is the AlphaGo system. So you probably have heard of this algorithm that you might develop that plays Go and beat what was considered the world champion. And so how does AlphaGo, in particular AlphaGo Zero, work? There's two components in AlphaGo Zero. The first is the neural network, which combines the policy and the value network. So the value network in Go, there's only one reward: do I win the game, do I lose the game. And so the value network says, based on the current state of the board, what is the probability of winning the game? And it tries to regress because it knows at the end of the game who wins, and it tries to say, could I have predicted this? I will not say that yet how the policy network trains, but the policy network tries to predict what is intuitively a good move to the network. But to know how you train the policy network and how you actually use this, well, there is a form of tree search that uses the model of the game. Of course, it's a very simple model because Go is a symbolic environment for which we could put the rules of the game in. But effectively, tree search is a form of reinforcement learning because it knows what are the consequences of the action. If I take this action, the state of the board changes this way. If the opponent takes this action, the state of the board changes this way, which is much less clear for, let's say, a robot that interacts in a physical world. But it uses the tree search to effectively uses the policy network to create candidate positions, candidate moves, and uses the value network to evaluate the leaves of the network to say, well, this whole branch seems pretty promising. This branch doesn't seem very promising. And by doing so, it tries a lot of action. It tries to imagine a lot of possible scenarios of how the games would go, and uses this tree to generate good actions for the policy network to learn from. So instead of the policy network learning by trial and error, what it does is try a bunch of action, quote unquote, in the simulation in its head, and sees which action led to a good outcome. This particular lead of the game is plausible because it corresponds to move the opponent I would want to make and the opponent would want to make, and I won the game here. So the first move is a good move, and that's the kind of move I should try to do more often. And it also generates action using action. Okay, so now of course, now for the Zero, the benefit is that the rules of the game were encoded in the algorithm. So when we learn the rules of the environment, how do we build mental models? That's a complicated question. What does it mean to build a mental model of the world? So here is, I don't think he was talking about this, but Feynman said, well, I cannot create, I cannot understand. So maybe one operational definition of a mental model would be that we are able to create, so basically we want to reverse the error of supervised learning. So supervised learning says, this image of a horse exercises a horse. If I give you the word horse, can you imagine? You draw effectively a horse, but of course not just one horse, otherwise you're just a picture book. You need to be able to create a variety of horses. So you need to effectively go from a single instruction and be able to create a stochastic, correlated, and high-dimensional model. So here is a possible definition of a mental model. It's the ability to generate or simulate your own sensory experiences. Ultimately, the agents, it's grounded by sensory experiences, and so if I would want to regenerate my sensory experience, I mean, I understand the world, I will simulate the consequence of my action at a sensory level. So this brings me to give a very quick introduction to generative models, which are the kind of neural network that can create this kind of sensory experience. The way they work is that they're typically given two inputs. One is the context or instruction, for instance, force, and the other is the source of a random vector. And you can think of this random vector as a source of body that the neural network is going to learn to shape through nonlinear transformations into a desired output. So this whole field, I don't explain how you train it. This is very complex, but this whole field is making a lot of progress. It's in a sense harder than supervised learning because you go from something simple to something very complex. But it's making a lot of progress. So these are examples of samples from a paper by Van der Oort in 2016, which are samples of potential images of horses. This can be used indefinitely for the domain of application because there is no kind of structural assumption made in a network because it's a very general framework. There is nothing in the network that was designed for horses in particular, so it can be used, for instance, for images, it can be used for sound. I won't take this example for much time, but basically without any kind of knowledge of voice synthesis or musical synthesis, by just training on large amounts of data, you're able to get state-of-the-art synthesis of images actually in Google phones. You can create music as well. 2017. Okay. These images are coming from a paper called Progressive GANs, which is from Carousel from NVIDIA. And these attractive people actually do not exist. It was the neural network was trained on a set of celebrities, and after that, after you train it, you can say generate more of the same kind, and you get these images of people that probably remind you of real people that are actually not real. So of course now these models of sensory experiences are not causal. There's no action in this. This is just kind of started. So next you need basically environment models. So these are simple images of an environment. I'll skip very quickly, but these are images of an agent that lives in some kind of 3D world, and these are generations of the agents, and by varying the random vector, the dimension of the random vector, you can see that you control different factors of variations, like the distance, the identity of the object, the rotation, and so on. This can get back to this kind of images, but it can get back to images of a robot, so you can actually find that the embedding of the network corresponds to the wrist turn of the manipulation arm, the vehicle arm, and the different dimensions correspond to whether the arm is up or down, if it's to the far, if it's right or left. Okay, so now to integrate with RL, we need to have an environment model that takes into account actions. So this is the kind of neural network we're training for that purpose. The idea is that when you try to create sequences of sensor observation which are conditional on action. So this is very much effectively the marriage of deep neural networks, and if you know what that is, a common filter. So there is a notion of state, which is some kind of abstract representation of what's going on in the world, and the state gets updated by feeding what action the agents took, some randomness which will be shaped by the network, and this state can be decoded to this sensor observation. So the hope is that while this is an image, maybe this contains information about the kind of objects which are in the scene and their position and their velocity, but it's very depending on the kind of environment. And you can, for instance, use it for the game of Pac-Man. So these videos are, there are two videos where it's the same exact sequence, the same initial state, the same sequence of actions, but I'm learning very slowly. And so these are actually generated artificially by the neural network. And so you can see that here the agent understands, quote unquote, what would happen if it went up, if it went down, if it went right. And the reason that we have two videos here is to show that it also understands that there is variability in the environment, that I cannot predict exactly the movement of the ghost. Or if I show you this frame, you will not know exactly in which direction the ghost goes. You have a pretty good idea, but there is randomness. Okay. A little bit further. So now, how do you actually use these models? I've only told you how you can create effectively models of the world that understands the causal relationship between actions and the change in the state and the change in your sensory experience, but how you use them. So we've been working on effectively integrated environment models with planning, and one big difficulty of environment model, the conceptual difficulty of using model based on reinforcement learning for real problems, is that your models will always be inaccurate. You're simulating something which is highly complex. In my head, there's a little simulation of what the world looks like, but it's certainly not like the super high accuracy physics simulator. I have some idea of how people react based on the theory of mind, but it seems it's very imperfect. And so the common issue with classical model-based RL is that if you use your model as a replacement for reality and you train on that, you will tend to overfit the model. You tend to start to trust your model too much. You start your mental model of the world, and you make mistakes in the real world because that is much. So what we do here, I won't get too much into the details, but we basically use the model as an oracle you can ask questions to. Then the neural network learns to interpret the answers. It knows the neural network is designed in such a way that there is an ability to potentially mistrust the model if it makes wrong predictions, and to only extract relevant data information provided by the model. And we've dived into two problems. The game here you see is called Sokoban. You may have played before. It's a complex planning problem where you have this little green alien here who has to push boxes onto these targets. But the alien can only push the boxes, it cannot pull them, which leads to potentially a lot of irreversible decisions. And irreversible situations are the ones where you want to think carefully about your actions. And it's a challenging game. I mean, like if probably a human that plays the game often can solve most of the levels, but it takes some thinking. And so this is your visualization of the agent taking a break and visualizing potential different futures based on different type of you have different rows for the different types of actions you're considering, and analyzing those situations. So for instance, here, a mistake could be that this box is in the target. I want to get out of here, so I'm going to push this box on the left and push this box there, which all that is a good situation because we only have two boxes on the target. But unfortunately, if this box is moved on the left, it's stuck in the corner and never getting out also the left. So you have to actually get out of this corner, which is desirable, and push this box further, which is what I would there with you. And you can see it considers both. If you're pushing the box forward, also consider pushing the box on the left, and then you can see here that even though it looks pretty decent here, you have 3 boxes in the target, you have one you can never get out. And extract that information from these simulated observations and realize it's not. Okay, so very quickly, I'll skip that, but the high-level story is that if you use Model 3 method in this kind of problem, you only can solve 60% of the levels. If you use Model-based methods and plan, you can go from higher to 80 and even 90% of the levels. You can also apply to Pacman, and I showed Pacman as an example because Pacman is actually a game for which Model 3 methods cannot do very well. Essentially because there's an aspect of planning and trying to understand where the ghost is going to go and what have the time to make that turn and so on. It also leads to higher performance and now superhuman performance in Pacman. Now, it's been applied. This is a paper from a few weeks ago, actually, by David Hein and Jürgen Schwinuber in Google Brain in Switzerland, where you can see that they train here. This is the real data on the left, and on the right is basically a simulation or hallucination of the data. And they use these kind of approaches to solve this car racing problem. And they also use some kind of like shooter game, so it's not a violent version in the sense that you're not shooting anyone, you're trying to avoid being shot at. So on the left you have the task, the aliens are shooting at you, and potentially avoiding it, it's a little bit like baseball, you make a visualization of the thing coming towards you, and you have to time your avoidance. And it's quite interesting what they do here because they actually use this to train on completely hallucinated data. So it leads to far better data efficiency because they don't use real world experience. The agent is training quote-unquote inexperience in simulated data and uses that replacement data to actually learn. Okay, so now you can say, well, what this one thing that is not addressed is, I'm almost done. Get out of the side. Sorry about that. All right, so you can say, well, what does that have to do with common sense understanding, world understanding? This is, Pacman is not the real world. And of course, I'm not entertaining that. The idea behind doing stuff in Pacman is that Pacman is kind of an ontologically consistent world. There is Ghost, there's Pacman eating big pills allowing you to use the Ghost, and so there's a set of rules, and we don't want to put these rules to learn them. But the kind of methods that you apply in Pacman can be applied to potentially completely different problems. And the question is, what is the environment you're trying to solve problems in, and what are the rules of this environment? Of course, if you're trying to do robotics, the rules that you care most about are effectively physics. And extremely similar neural networks, very, very similar neural networks, can be used to effectively do video prediction of robotic arms. And again, there is no prior knowledge, no physics encoded in these models. They're trying to learn end-to-end what objects look like, and kind of effectively a version of intuitive physics where you have this, it's hard to say this is pixelated, but this arm is moving this ball, and it understands that objects are permanent and that they move and that there's collision and what roughly the rules of physics of that particular environment are. And closing the loop, those people, Chelsea Flynn, Sergey Levin, and Pierre Diel, are using these kind of methods to try to do planning in simulated robot environments. The reason that simulation dominates a lot of this field is because it's a very cheap way to get a lot of data. Robotic data is expensive for a variety of reasons, but in great part because we want to break it off. That's the kind of methods that work in simulation tend to work very well in the real world as well. It's just data is more expensive. And so they use the method, this kind of simulators here that I mentioned, to try to model Quasar in this kind of complicated grasping tasks. And you can see that the models essentially look very much like real robots. Okay, so I'm done. In conclusion, so Model Quasar is one venue to endow agents with a mental open world. We're only scratching the surface, and there is a lot of problems remaining to be solved by the entire community about how to do modeling, world modeling, and how to use these world models to train better. Work needs to be done. It's also by no means the only method that is possible to RL. There's a lot of things that I don't have any time to talk about, mid-reinforcement learning, and supervised learning, RT for RL, athletic RL, and so on. And all of these institute venues to try to put the arts in control.
Thank you very much.